Okay, so in this video, we will consider the following problem. What if we have a curve in the xy plane that is not given explicitly as y equals f of x, but as an algebraic equation involving x and y? So if we do not have y equals f of x explicitly, can we still find the derivative of such a curve? And at a given point, can we find the equation of its tangent line? Let's consider a very simple example that will illustrate the idea. Suppose we consider a curve, C, given by the following equation. We'll take x squared plus y squared is equal to 25. Notice that 25 is 5 squared, so the equation is x squared plus y squared equals 5 squared, and as you should know, this is a circle centered at the origin of radius 5. So let's sketch this curve. And why do I use the word curve and not function? Well, it will be apparent once we actually sketch the object. We have a circle of radius 5 centered at the origin. So you see, a function has as a defining property for any given value of x, there exists a unique y value. We'll take any given x other than 5 and negative 5, and you have not just one value of y, but two values of y. So you see what we have here is a curve, not a function. What if we asked, well, can we find the derivative of this curve, right? If you take any point on the curve and draw its tangent line, the slope does exist, and we're asking, well, can we find it? And the problem we have right now is this looks slightly not familiar, right? Usually we have a function y equals f of x, and then we find the derivative the old-fashioned way. But here, we don't have y equals f of x. We have x squared plus y squared equals 25. Let's cheat here. Let's try to find a way to solve for y and see how many curves are building, how many functions, are building this curve. So let's try to isolate for y here. If we do, then we'll have y squared equals, subtract x squared on both sides, so y squared equals 25 minus x squared. And here be careful, if y squared equals this, then y will be, because once you square something you kill negative signs, so y will be plus or minus the square root of 25 minus x squared. And you see we have two functions. And if you look at this, when we take the positive, we get positive y value. When we take the negative, we'll get negative y values. So if you look at your curve, well, the upper semicircle is given by picking the positive, so we'll get y is equal to the root of 25 minus x squared. And so this function now, the upper semicircle, gives you half of the curve, and the lower semicircle, of course, is given by the negative. So you see, the algebraic equation x squared plus y squared equals 25 is not a function, because for any given x value, there are two y values, but this curve is built from two functions. This function gives you the upper half of the semicircle. This function gives you the lower half of the semicircle. And now we can find the derivative. Let's find the derivative of the upper half of the semicircle. So we have y equals this. So dy over dx is the derivative of the function root of 25 minus x squared. And I'll rewrite the square root as a power of 1/2. So let's differentiate. Well, if I give you an x value, you will first square it, then do 25 minus that value, and then take the power of 1 over 2. So by the chain rule, we have to differentiate the outside function first. The outside function here is the power of 1/2. The power rule says bring the power down. subtract 1 from the exponent, 1/2 minus 1 is negative 1/2, at whatever is left over, so 25, minus x squared, and that takes care of the derivative of the outside function. If there's anything left over, the chain rule says you have to multiply what you have so far by the derivative of what's left over. Well, the derivative of 25 is 0 minus the derivative of x squared, which is 2x. So we have minus 2x. There's nothing left over, so we are done differentiating by the chain rule. Let's simplify a little bit. Well, negative 2 over 2 is negative 1. You can cancel the 2. And that will send a negative exponent on the bottom of our fraction, so the negative 1/2 will become a positive 1/2. So we'll have negative x over 25 minus x squared to the 1/2 power. And now I'll replace the 1/2 power by the square root, so I get negative x divided by the square root of 25 minus x squared. And we have the derivative of the curve for the first half. You can do the same thing for the second half, the bottom half of the curve, and that works the same way. Now, if you look at this, there's something worth mentioning here. There's something interesting about the expression. Remember that for the upper half of the semicircle, y was equal to root of 25 minus x squared. And if you look here, that's the root of 25 minus x squared. So that's just equal to y. And we make then the expression even simpler. Negative x over the root of 25 minus x squared, which is simply y. And now, if we summarize, we have that the derivative of the curve, dy over dx, happens to be negative x over y. What's great about this, and I'll let you verify yourself, if you find the derivative for the second half, the lower half of the semicircle with this equation, you will find, interestingly enough, the same result. dy over dx will also be negative x over y. So for any point on this curve, this is the derivative. Now, let's find a given point on this circle and find the equation of its tangent line at that point. Well, if you look at the equation of the circle, it's x squared plus y squared is 25. If you take the point x equals 4, y equals 3, 4 squared is 16, plus 9 squared, right, if you check here, 4 squared plus 3 squared is 16 plus 9, which is 25. So the point x equals 4, y equals 3 is a solution to the equation of the circle, hence we have a point on the circle. And we can draw the tangent line to the circle, and we can ask at this point, at the point x equals 4, y equals 3, what is the equation of the tangent line? Say y equals mx plus b. Well, let's see. We have the derivative of the circle at any given point xy. So, if you recall, y, our tangent line, is given by mx plus b. And the point of interest is the point x equals 4, y equals 3. Well, as always, the slope of the tangent line is just the derivative of the function. So here we have m equals the derivative of the curve, specifically at the point of interest. And the point of interest here is x equals 4, y equals 3. Well, the derivative we found to be negative x over y. So this is negative x over y evaluated when x equals 4 and y equals 3. And now we just replace. Negative x, well here x is 4, that's negative 4, over y, which equals 3. So the slope of our line is just negative 4/3. And the slope being negative is expected. From the picture, we see that we have a line with a negative slope. And now we can find the equation if we find our b, right? Now y is m, which is negative 4/3 x plus b. And we know that the point 4, 3 is a point on our tangent line. So it has to solve the equation of the tangent line. So we substitute x for 4 and y for 3. So we get 3 equals negative 4 over 3 times x, which is 4, plus b. But negative 4 times 4 is negative 16 over 3, plus b. And that's equal to 3. So add 16/3 on both sides. So b equals 3 plus 16 over 3. Well, put this 3 over 3, it's 9 over 3. So it's 9 over 3 plus 16 over 3, which gives you 25 over 3. And this is your value of b. So our conclusion is that the tangent line is given by negative 4/3 x plus b, which is 25 over 3. And we have the equation of the tangent line to the curve that is a circle of radius 5, centered at the origin at the point x equals 4, y equals 3. There is a problem here, and the problem is we cheated, right? It was a lucky example where even though on the surface we weren't given y equals f of x, we were able to find it and then find the derivative the old-fashioned way. But the question is, what if we had a slightly more complicated equation for the curve? What if it was impossible to solve for y explicitly as a function of x? As it turns out, it almost always is the case. If I give you a random equation involving x and y, and I ask, can you solve for y as a function of x? The answer is almost never. So let's try and find the derivative, dy over dx, as negative x over y, but without cheating, without solving for y as a function of x. And the idea is what we call implicit differentiation. So we only want to look at the equation of the curve and not cheating and solving for y as a function of x, because very often this is not possible. But the key idea here is to remember one thing. Even though on the surface you do not see y equals f of x, y really is a function of x, depending on where you look on the given curve. So you see, if you look at this part of the curve, y is this function of x. If you look at another part of the curve, y is this other function of x. And this is true of all curves. You see, this curve is made up of two functions, the upper semicircle and the lower semicircle. A curve may be built up from 20 different functions, but wherever you look, y will be a function of x. So the key is, even if you don't see y equals f of x, you can still think of y as a function of x. And that is the idea of implicit differentiation. And now let's do it this way. Let's find the derivative of our curve, not by looking at y explicitly as a function of x, but thinking that y is a function of x. So we have the curve given by the equation x squared plus y squared equals 25. And now again, we will not cheat here and assume that we know that y equals a particular function of x. But we'll say, let's think of y as a function of x. So suppose that we say, well, y is some function of x. If you look at locally a point around the curve, y will be a function of x, right? If you look at this part of the curve, y equals this function of x. if you look at other points on the curve in the lower semicircle, y is this other function of x. But if you look around a point, y will be given by a unique function of x. And now let's differentiate x squared and y squared very carefully with the chain rule. And then we'll move on from there. If I ask you the derivative with respect to x of x squared and the derivative with respect to x of y squared. Let's go over both very slowly, thinking of the chain rule and thinking that we differentiate with respect to x. So in both cases, we have x squared, y squared, so the outside function is the power 2. So we use the chain rule, power rule, bring 2 down. Subtract 1 to the exponent. 2 minus 1 is 1. This takes care of the outside function. 2 times what's left over, x. 2 times what's left over, y. And now if we apply the chain rule, we have to multiply what we have so far by the derivative with respect to x of whatever is left over. Well, here what's left over is x. Here what's left over is y. And now by the chain rule, there's nothing left over, so we're done differentiating. And let's see what we have now. We have 2x times the derivative of x with respect to x, but the derivative of x is simply 1, so we're left with 2 times x. And now let's look at this case, 2 times y times the derivative of y with respect to x, dy over dx. But since we don't know what y is equal to as a function of x, we'll leave it as the derivative of y with respect to x. And that is our unknown. So we don't know what it is. But the key is that's what we're trying to solve. And now from these two equalities, let's see how we can find our dy over dx without having to know what f of x is. The idea is actually quite simple. You have an equality, so x squared plus y squared equals 25. Well, what is the implication here? If both sides are equal as functions of x, right, because y is a function of x, even though in this case we don't know exactly what it is, we still think of y being a function of x. So what we have is this function of x equals this function of x. So if both sides are equal, they must have the same derivative. And now let's differentiate and see what comes out. The derivative of a sum of two functions is the sum of the derivative. So this will be the derivative of x squared with respect to x, which we have just found before is simply 2x, plus the derivative of y squared with respect to x, which we have found to be 2y times dy over dx. And that takes care of the derivative of the left-hand side. And this is equal to the derivative of 25. 25 is a constant, its derivative is 0. And now look at what we have. We have an equality where we know everything. We know x, we know y, and we are trying to solve for dy over dx. dy over dx is the unknown. Well, we can easily solve for dy over dx with our equality. Subtract 2x from both sides. You'll have that 2y times dy over dx is negative 2x. You can cancel a 2 from both sides, and you're left with y times dy over dx is negative x. And finally, divide both sides by y, and what do you get? dy over dx is negative x divided by y. Just as before. And you see what's great here is that we didn't cheat. Nowhere in our solution did we assume that we knew what y was equal to f of x explicitly as a function of x. The idea is it's enough to think of y as a function of x. So when you differentiate a term with respect to x and there is a y, be very careful to complete the chain rule. And then when you have your curve, both sides are equal, differentiate both sides, you will have an equality that will allow you to solve for the derivative dy over dx, which as before, we found to be negative x over y. In our next video, we'll look at another example of finding the derivative of a curve without solving for y explicitly as a function of x.